Welcome to the deep dive. You know, the speed of AI development these days is it's really something. And the amount of information these models are expected to handle keeps ballooning,
It really does.
which brings up this big question. How do we actually get these powerful AI models to think more deeply, more efficiently, especially when you throw massive data sets at them?
That's a central problem right now, definitely. Particularly for the kind of tasks that need, serious reasoning over really long stretches of information. We're moving past simple lookups.
Right, into complex problem
Yeah,
solving.
multi-step stuff.
And that is exactly what we're digging into today. We're unpacking a really interesting new model called MiniMax-M1.
Hmm.
It's being called the world's first open-weight, large-scale reasoning model. And it specifically tackles this challenge of scaling what they call test-time compute.
Which is basically how much thinking time or computation the AI can dedicate when it's actually generating a response.
Mhm.
Got it. So our mission today is to explore its architecture. It's a hybrid,
Yeah.
which sounds intriguing. We'll look at the clever ways they trained it and see how its performance benchmarks are kind of setting new standards for AI agents.
Right. The goal is to give you a clear picture of what makes MiniMax-M1 stand out, especially if you're trying to keep up with all the rapid advancements in AI.
Okay, let's jump straight to that core innovation then, the architecture and its efficiency. You said it's a hybrid powerhouse. What's under the hood?
So fundamentally, MiniMax M1 combines two things: a mixture of experts or MOE design and something they're calling a lightning attention mechanism.
Okay.
It builds on their earlier model, MiniMax X01. Now that one was huge overall, 456 billion parameters total. But M1 is designed to be efficient. It only activates a small, relevant fraction of that for any given token.
Like finding just the right page in a giant library instantly.
Sort of, yeah, a good analogy.
And this lightning attention, what does that actually do? Sounds fast. It's built for speed and efficiency. It's an I/O-aware implementation, meaning it optimizes how data moves in and out. Think efficient memory access during those long computations.
Okay.
And the hybrid design is quite specific. You get 7 transnormer blocks using this efficient lightning attention, followed by 1 traditional transformer block with the more computationally intensive softmax attention.
So a mix of speed and focused power.
That seems to be the idea. Balancing efficiency for long sequences with the focus power needed for complex steps.
Now, one of the really eye-catching things is the context length. It supports 1 million tokens natively.
Yeah, that's a standout feature. 1 million tokens.
How does that compare?
Well, it's about 8 times the context size of something like DeepSeek-R1. And really, it's an order of magnitude bigger than any other open-weight, large reasoning model out there today.
Wow. So what does that let you do?
It means it's incredibly well suited for tasks that need to process very long inputs. Think analyzing long legal documents, understanding entire code repositories, maybe synthesizing information from dozens of research papers at once.
And this long context stability, it links back to the efficiency, right? The lightning attention enables scaling this test time compute you mentioned.
It does. That mechanism is key to handling such long sequences efficiently during generations of reasoning part.
How efficient are we talking?
The paper gives some numbers. Compared to DeepSeek-R1, MiniMax-M1 apparently uses only about 25% of the FLOPs, that's floating point operations, when generating a response 100,000 tokens long.
Only a quarter of the compute.
Yeah. And less than half the FLOPs at 64,000 tokens. That's a pretty substantial drop in computational cost.
Which makes it cheaper to run for inference.
Right, when it's actually doing the work. But also really important for the training phase, especially the reinforcement learning part, which is notoriously compute intensive.
Okay, let's talk about that training. Because getting these models to reason well often involves some complex training recipes. What were the steps for MiniMax M1?
It started with a foundation. The previous model, MiniMax X01, went through what they call continual pre-training. They fed it an additional 7.5 trillion tokens.
7.5 trillion.
Trillion, yeah. And this data was specifically chosen to be reasoning intensive. They curated it carefully, increasing the proportion of STEM subjects, code, and general reasoning data to about 70%.
And they also had to manage the context length during this phase.
Right. They didn't just jump to 1 million tokens. They extended it gradually in stages like 32K, then longer, up to 1M. This was important to avoid training instability, things like gradients exploding.
Makes sense. After pre-training.
Then came supervised fine-tuning, or SFT. This stage is really about teaching the model specific patterns, particularly chain-of-thought reasoning.
Like showing it how to think step by step.
Kind of, yes, showing it examples of that process. And about 60% of the SFT data was math and coding problems to really drill those logical steps.
So that lays the groundwork. Then comes the reinforcement learning, the RL stage, which is often where reasoning capabilities get a big boost.
Exactly, RL is critical. But standard RL algorithms, like PPO, have this issue. They sometimes clip out or suppress low probability tokens during training.
Tokens that don't seem likely.
Right. But the thing is, some of those low probability words can be really important for complex reasoning. Think transition words like however, or reflective pauses like wait, recheck, maybe even aha moments.
You don't want to lose those.
Especially not in these hybrid architectures. Clipping them can mess with the learning process, destabilize things.
So MiniMax-M1 uses something different.
They introduced a new RL algorithm they developed called CISPO. That's Clipped Importance Sampling Weight Policy Optimization.
Okay, CISPO. How does it avoid clipping those important tokens?
Instead of clipping the updates based on token probability, CISPO clips the importance sampling weights. It's a bit technical, but the upshot is that it ensures all tokens, even the low probability ones, can contribute to the learning gradients.
So it listens to all the signals, even the faint ones.
That's a good way to put it.
Yeah.
And they ran a controlled study using other models and found CISPO gave about a 2x speedup compared to another method called DAPO. It seems to reduce variance and make RL training more stable.
Interesting. Were there other technical hurdles they hit when applying RL to this specific hybrid architecture?
Oh yes. Scaling RL is never straightforward. One big one was what they called a computational precision mismatch.
Meaning?
They found that the probabilities a model assigned to tokens were different during training compared to when it was actually running inference.
Yes.
A significant difference.
Like the model wasn't seeing things the same way during learning versus performing.
Something like that. It hampered the reward signal, made it hard for the model to learn effectively from the RL feedback.
How did they fix it?
They increased the numerical precision of the final output layer, the LM head, to FP32. That brought the correlation between training and inference probabilities way up, from around 0.9 to 0.99. Much better alignment.
Okay, precision matters. What else?
Optimizer settings. The AtomW optimizer they used needed very careful tuning. They noticed the gradients, the learning signals were all over the place, sometimes extremely small.
So tiny adjustments needed careful handling?
Extremely careful. They ended up using specific values for the beta 1, beta 2, and epsilon parameters in AtomW to stabilize training with these wide-ranging gradients.
And you mentioned earlier this interesting problem of repetitive outputs.
Yeah.
The model getting stuck.
Right. That could really destabilize things, especially in RL, where you might get these pathologically long, repetitive, low-quality responses.
Like a feedback loop gone wrong.
Potentially. So they put in a heuristic, basically a rule of thumb. If the model generates 3,000 tokens in a row, and each of those tokens has a probability over 0.99, it just stops.
Cuts off the loop.
Exactly. Prevents it from going off the rails and improves efficiency by not wasting time on those repetitive sequences.
So with CISPO and these fixes for the hybrid attention issues, they managed the RL training quite quickly.
Relatively speaking, yes. They reported completing the full RL training for MiniMax-M1 in just 3 weeks.
Using how much compute?
512 H800 GPUs,
Oh.
which is a lot of firepower.
Wow. Any estimate on the cost?
The paper mentioned an approximate rental cost around $534,700 USD for that 3-week period.
Okay. So significant investment, but fast turnaround thanks to the algorithmic efficiency and hardware.
Seems that way.
Let's shift to the data used for that RL training. You mentioned it was diverse. What kinds of tasks did they feed it?
They used 2 main categories. First, what they call rule-based, verifiable tasks. Things where you can clearly check if the answer is right or wrong.
Like math.
Definitely. About 50,000 competition-level math problems, filtered by difficulty. Also, logical reasoning, they synthesized around 53,000 samples for things like cipher puzzles, Sudoku, using a framework they built.
Synthesized, so AI-generated logic puzzles.
Seems so. Configured for appropriate difficulty. They also included competitive programming problems, about 30,000 of them. And interestingly, for software engineering tasks, they used real-world GitHub issues and pull requests from a benchmark called SW Bench. The model was trained in a sandboxed environment where it actually tried to fix a code and got rewarded based on whether the test passed or failed.
So direct execution feedback. Very cool. What was the second category of data?
Model-based feedback tasks. These are for more general domain things where there isn't a simple right-wrong answer determined by rules.
Like creative writing.
Exactly, or general instruction following. This category included tasks that do have a ground truth, like STEM questions or factual recall, where they use another AI model, a generative reward model, or GenRM to assess the quality.
And AI judging another AI's answer.
Basically, yes. And for tasks without a clear ground truth, like the creative writing or general instruction following, they use pairwise comparison data, human preferences, between two responses to train that GenRM judge.
Okay, but these reward models, especially for long answers, can sometimes develop biases, right?
That's a known issue.
Hmm.
They specifically mention tackling length bias. That's where the reward model starts favoring just longer answers. Even if they aren't actually better quality, it just learns longer is better.
How did they counter that?
They did continuous online monitoring during the RL training. If they detected the main model starting to just generate longer and longer stuff without quality gains,
They tweaked the judge.
they immediately recalibrated the GenRM. And they also used techniques on the RL side, things like reward shaping, value clipping, normalization, to steer the model towards substance, not just length.
So active bias monitoring and correction.
Yeah.
Smart. How did they blend all these different data types? Math, code, logic, general tasks.
They used a curriculum approach. Started mainly with the rule-based reasoning tasks to build those verifiable skills first. Then gradually they mixed in more of the general domain tasks using the model-based feedback.
Build the foundation, then generalize.
Seems to be the strategy. Using dynamic weighting to control the mix over time. The idea is to refine those core reasoning skills, but also make sure the model performs well across a wide range of tasks without forgetting the specialized stuff.
And they pushed this even further, scaling the length of the reasoning. You mentioned M140K and M180K models.
Right. The 80K model extends the maximum generation length to 80,000 tokens. That's the length of the AI's thought process or answer.
Not just the input context, but the output length, too.
Correct. And getting RL to work reliably at those generation lengths brought its own challenges. They used a staged approach again, expanding the window gradually, say, from 40K to 48K, then to 80K for stability.
What kind of instability did they see?
They mentioned something called pattern collapse. Basically, the generated text would become incoherent or nonsensical deep into the sequence, like after tens of thousands of tokens.
The model just loses the plot.
Seems like it. They found this was partly because negative or low-quality examples tend to grow faster in these long sequences during RL.
And the solutions?
Similar ideas came into play. Detecting repetitive patterns for early stopping, using careful normalization of rewards at both the sample and token level, and adjusting gradient clipping thresholds, fine-tuning the training dynamics for extreme lengths.
Okay, so a lot of careful engineering went into both the architecture and the training. Let's talk results. How does MiniMax-M1 actually perform?
Overall, the paper presents it as performing comparably or sometimes better than other strong open-weight models like DeepSeek-R1 and some of the Qwen models across a range of standard benchmarks.
Any particular areas where it shines?
They highlight a few. Software engineering seems strong. The M180K model got 56.0% on a benchmark called SWE Bench Verified, which they state surpassed other open weights.
What about using tools like an AI agent interacting with software?
Good results there, too. On TAU Bench, specifically the airline booking task, the M140K model apparently outperformed other open-weight models and even Google's Gemini 1.5 Pro, and the 80K version consistently did better than the 40K.
And long context understanding, given that 1 million token input window.
That's where it really pulls ahead of other open-weight models, as you'd expect. On benchmarks designed to test understanding over long contexts, like OpenAI's MRCR benchmark, the M1 model significantly outperformed others.
Any specific numbers?
Yeah, for example, on MRCR using a 128,000 token context, it scored 73.4%. And at the full 1 million token context, it got 56.2%. They note this even surpassed closed models like OpenAI's GPT-4 Turbo 01 version and Claude 3 Opus on some of these long context tests.
Impressive. Did they show that the longer thinking the test time compute actually leads to better answers?
Yes, they explicitly looked at this correlation. As the RL training progressed, allowing for longer average response lengths, the actual accuracy on benchmarks also consistently improved.
For instance?
On the AIME 2024 math benchmark, accuracy reportedly climbed from 68% to 80% as the average response length grew, eventually exceeding 20,000 tokens.
So allowing it to think longer really did help it solve those hard math problems better.
That's the evidence they present. It validates the focus on scaling that test time compute.
And is this model accessible for people to try or use?
Yes, they've made it available. It's on GitHub and Hugging Face, integrated with frameworks like VLLM and Transformers. They also mention a commercial API.
Good to know. So wrapping up then, MiniMax-M1 seems like a really significant development.
I think so. It
Yeah.
represents a solid step forward in building these large reasoning models that are not just powerful, but also efficient in how they apply that power, especially for long, complex tasks. The combination of the hybrid architecture and the refined RL techniques like CISPO is quite potent.
It really shows that scaling this test time compute, letting the AI think longer efficiently, is crucial for tackling harder, real-world problems.
Definitely.
So as a final thought for you listening, consider MiniMax M1's ability to handle these incredibly long contexts and perform extended reasoning efficiently. How might advancements like this change how we interact with AI agents down the line? Think about complex workflows, scientific research. Where could this deeper, more efficient thinking make the biggest difference?